Cool. Welcome to the panel on designing computer systems for sustainability. My name is Carol Jing Wu. It's a great pleasure to be moderating this panel. I'm currently a research scientist and director at Meta's AI Research. I'm also the founding member and VP of ML Commons. And sustainability is something that I have been very curious about ever since as a student. And in recent years, it is clearly becoming that this is an urgently important issue facing our society, and also something that computing industry can contribute to. So in this panel, we are going to look into what designing next generation computing infrastructures means when we take into account sustainability and how to go beyond efficiency. My goal with the panel here is to bring sustainability into the ISCA community and have a conversation on why sustainability is relevant to computer architects and how computer architects can contribute to advancing the state of the art. I want to acknowledge that there are many different environmental resources that computing uses, but today we are going to first focus on carbon emission. This is immediately an aspect that ISCA can contribute to. The scope of this work is very broad. We will first take a look at the energy use and carbon footprint of computing across its entire life cycle. And then I want to encourage everyone here to continue discussion with the panelists and with attendees beyond this panel itself, during the banquet, the excursion, and throughout the conference itself, such that you can bring new ideas and form new collaborations in this very important interdisciplinary domain. I also want to mention that there are new funding opportunities that's coming up in case you are looking for support to work on this problem space. So first, we're going to take a look back, and before we look forward on where our computing industry is at. First, efficiency has been something that keeps the ISCA community busy, and this is also what's keeping computing's electricity demand constant. So in this science paper that was published at around 2020, the researchers have looked at what is the carbon footprint or electricity use of computing instances like. And what they found is that between 2010 and 2018, we are able to scale up compute instances by 550%, while the electricity usage only increased by 6%. They also did the projections on how we will be able to double computing instances without increasing energy usage very much. Well, that was the story in 2020. Between 2020 and today, I guess there is the ChatGPT moment that is impacting many different aspects of our life. So in this subsequent paper, the researchers then make projections on how, because of ChatGPT and new generative AI technology that comes to the computing industry, we are going to see energy usage to double, actually. In fact, if you pay attention to the growth of hyperscale data centers, by digging into the electricity demand of data centers over time, you will see that data center electricity usage by Google, Microsoft, Meta have been increasing very quickly. And in my own MLSys 2022 paper, I talk about how AI is driving this increase in energy usage across the dimensions of data, model sizes, and compute instances that's installed into hyperscale data centers. Everything has been increasing in an exponential rate. Recently, you may come across this article published by Bloomberg. It's very interesting to see how hardware architecture has become dramatically energy efficient and is becoming smaller in size, but the overall data center energy usage has been increasing. On the x-axis, you can see it's in log scale, and the amount of land required to build these data centers is also used in an exponentially increasing rate. Okay? And energy usage is only one aspect of computing's overall life cycle. If you look at the entire life cycle of a computer devices using this LCA methodology, you will see that the energy used during the product use phase will come with operational carbon footprint, which is determined by how energy is being produced in the power grid and therefore consumed by data centers. But before these computers get installed in data centers or being plugged into the wall, there is all the additional energy used in order to manufacture these computers. In fact, wafer manufacturing is a very electricity-intensive process. It also produces a lot of chemical gases. On top of that, there is also all the e-waste that get produced at the end of the computer's life cycle. And so there is all the additional emissions that can come from the end of life cycle processing. Now, let's take a look at how significant these other aspects of computer systems can look like. This is an analysis that I did with colleagues at Meta, researchers from Arizona State and Harvard University. We dig into many publicly available sustainability reports published by Apple. And what we found is that across Apple's consumer electronics devices, about 74% of their overall emission is coming from manufacturing. 33% of which is coming from manufacturing of application processors, DRAM, storage devices, and only less than 20% is coming from operational use phase. And so there is this roughly 80 to 20% breakdown. And we expect that with advanced process technology, it's going to become more important as we go forward. Embodied carbon footprint is going to increase, both from electricity usage perspective when we scale from 7 nanometer to 2 nanometer, and then as we also the chemical gases that get produced between these different technology nodes. Looking forward, the next wave of computing devices is going to have an impact as well. Today, we have smart glasses, but tomorrow we are going to have augmented reality at the scale of billions of users. When we start incorporating these additional computing capabilities, these additional embodied carbon needs to be accounted for. So now we have a very quick peek at the lay of the land on computing's environmental implications. I would like to welcome 4 experts that has been looking at computing's environmental implications. And I would like to first welcome Tamar Ilam. Tamar is an IBM Fellow and a Chief Scientist for Sustainable Computing at IBM T.J. Watson Research Center. Tamar is leading the research aimed at drastically reduce computing footprint associated with infrastructure, systems, software, and AI data usage. Next, we'll have Babak Fasafi. Babak is a professor at EPFL. He is also the founding president of Swiss Data Center Efficiency Association. And this is a industry-academia collaboration consortium that looks into certifying full stack efficiency and emission in data center computing operation. He is also the founder of EcoCloud. And this is a research center at EPFL that looks into sustainable information technology ever since 2012. Next, we have Gage Hill. Gage Hill is an assistant professor of electrical engineering at Harvard University. His research focuses on developing energy efficient and environmentally sustainable computing systems. He looks into how to combine new technology advances across nanomaterials, devices, sensors, circuits, architecture, and integration techniques. Finally, we have Bobby Manet. Bobby is no stranger to our computer architecture community. She is a senior fellow at AMD Research and Advanced Development Center. She's been analyzing efficiency and sustainability issues in CPU and GPU designs. Let's welcome our panelists. Okay, we have a few questions to seed discussions, and I also want to encourage attendees here to sort of think about what questions that you have for us, and then later we'll have Q&A sections. Right? So first, thanks for contributing to this panel. Can you please share with us, and also the audience of the panel, what does designing computer systems for sustainability mean to you? And if you can also share with us what you see as new challenges by bringing sustainability into the computer architecture community.
Should we go? Does this work? Okay, yeah, well,
Yeah.
Thank you very much for this panel introduction. What we're seeing in the data center space today is that one of the fundamental challenges is properly identifying when we deliver a kilowatt hour of electricity to IT equipment, exactly what the output of that kilowatt hour is. And this community is at the center of this challenge. We can look at solutions with proper metrics, proper instrumentation, proper ways in which we can say, look, when we deliver electricity to our computing, with this electricity, we're going to get this kind of outcome with this level of efficiency. And that's something that's missing from computing today. And in the data center space, everybody's heard about PUE. PUE is just a fraction of electricity that goes into the housing infrastructure, cooling, electrical subsystems. And PUEs, hyperscalers have had PUEs close to 1, and co-locators have PUEs that are around 1.2 and going lower. Most of the electricity is getting delivered to IT. Nobody knows what's happening to that electricity.
All right, let me go next. So I think it's really important to look at the trends because it's really illuminating. So there are multiple points of evidence that data center energy is on the rise. But what's important is to look what's behind it. So I think everyone understands that it's a conjunction of two different phenomena. One is the end of Dennard scaling, and the other one is the rise of AI, specifically generative AI, and which is very energy intensive, and the high popularity of it, which really conflicts with our net zero, global net zero aspirations. And these two phenomena together obviously gives the rise to extreme specialization. For obvious reasons, we can only gain energy efficiency but with specialization, but we need to lose generality for that. However, the dark side or the pitfalls of specialization, I think we need to look at the hidden cost here. And what I'm saying is two different things in hidden cost. One is the hidden cost of carbon. So as the complexity of the system rises, also the manufacturing complexity, and Carol alluded to this, like with edge devices, 70 to 80% is the embodied carbon emission, which is the cost to design and manufacture a system, but not only with edge devices. It's very significant, and it's much harder to handle because it's becoming more significant because of the penetration of renewable energy. However, renewable energy can do so much for manufacturing because manufacturing also involves gases and things like that. Okay, so that's one. Carbon cost must be factored in. The other one is the rise in complexity. So when we have this diversity of hardware and software, which are very diverse, hardware proliferation, and then software, even if you look at just AI or just Gen AI, depending on the model architecture, the number of layers, the weights, and the parameters, the weights, the sparsity, and so on, the behavior is going to be completely different. Okay, so complexity of hardware and software design, complexity of packaging and integration, just to make it all work together, it's very hard to get it right in terms of the balance of resources. So you may end up having, for the typical workload, you may have stranded resources, unexpected bottlenecks, and so on, and benchmarks can only do so far for you. Then when you get to the runtime, it's also complicated because then you're stuck with what you have, which is a bunch of accelerators, a data center that is much more heterogeneous, extreme heterogeneity, and much, much harder to manage. in order to actually get the efficiencies that specialization promised to give you. So this is the two problems that I see, the carbon cost and the increased complexity.
Yeah, I'm going to sort of tag off that a little bit more probably from the circuits side. So I consider myself to be an integrated circuit designer. I've actually never been to ISCA before, so it's actually great to be here. But sort of like tying to this, manufacturing cost, like when I see those curves that like, okay, the carbon footprint costs of actually like physically manufacturing this like 7 nanometer chip or 5 nanometer or like 2 nanometer chip, like that looks like a huge opportunity, like exciting opportunity for like an integrated circuit designer to actually have an impact there, right? Because we are like, and it's same with computer architecture, right? Like we're all like defining the structures that are actually getting like physically made on the chips. And so we can like, we have the capability to make trade-offs like, oh, we want to use maybe this type of memory or that type of memory, or we want to use this type of process or this circuit topology to actually like optimize, like trade off like the performance of the systems we're designing with the overall carbon footprint. So that sounds like a great, like exciting opportunity to me. The challenge there is like that I can't log into my tools and get very like accurate models for carbon footprint of the system I'm designing. Like like when I'm running like SPICE simulations or something, it tells me like exactly like in picoamps or femtoamps how much current my circuit is consuming like at every picosecond, right? Like I just don't have that level of granularity for like the carbon footprint of the system that I'm making, which makes it very challenging to optimize. So it's like you have both this technical challenge of like, even if you did have this carbon footprint model, how would you optimize your computing system? And then the sort of maybe even more logistical challenge, or something that needs some kind of policy or buy-in from companies to provide some kind of like equivalent like process design kit, but for carbon, something like that might be really helpful. Like getting the data sort of like accurate, like reliable data in the hands of designers, I think is a key challenge.
Oh, thank you. I see the computing industry as the poster child for the Jevons paradox, because basically over the last 50 years we have orders of magnitude improvement in the hardware, and we've done a tremendous job. It's phenomenal, and yet we have even more orders of magnitude in the acceleration of computing and its use in our everyday lives. So fundamentally, we've done an amazing job, but in the process we've also accelerated the use of computing everywhere. And the other side of the coin is that because we've done such a great job, people can write really sometimes inefficient software and have it run really well on our systems. So there is this combination of events that have combined together to create this problem. And honestly, if we keep doing an excellent job in making everything more efficient, how do we then not allow Jevons paradox to come into the picture again and just keep this acceleration of use continued into the future? I think that's one of the big issues that we face. So not only do we have to make computing more efficient, however you define that, embodied carbon, operational, et cetera, but how do we bend that, basically what's called the rebound, the Jevons paradox rebound, how do we bend that curve and keep utilization also at a stable level while we're doing these efficiency improvements?
Yeah, I guess I'm hearing a lot about the trade-off balance between operational and embodied carbon or energy usage. I'm also hearing about metrics, standard measurement, and be able to look at the whole life cycle to get there. I guess here are some of the perspective that panelists is sharing. I guess perhaps we move on to the next part, which we naturally segue into already. What do you like to see as the new contributions from our ISCA community in order to advance the sustainability aspect of computing? What do you see as what computer architects and computing people can do?
Okay, I guess I'll start again. So, yeah. I think large language models are fantastic. We have cracked capabilities that we hadn't been able to crack for decades, so to speak. But fundamentally, trying to use an entire GPU node with 8 GPUs and 10,000 plus watts to do one inference is not going to be scalable. So fundamentally, that has to change. We have to come up with smaller models that are just as accurate, or maybe tuned models. And there's a lot of amazing work going on out there in that respect. But that's one of the pieces that we need to kind of figure out how to do that much more efficiently, because the other side of the coin is that you're going to want to run those models on edge devices because of privacy and security reasons. And I think that's going to be one of the most interesting areas of research, is not only how to make this efficient, but how to also run it on these devices like a cell phone, where you can charge cell phones, millions of times for the same power it costs to run a GPU for a few days.
Yeah, I can go again. Let's see. I had something in mind that I was going to say. Oh yeah, so I think it's not just ISCA that needs to do this, and the sort of parallel that I feel keeps coming up is this parallel to this whole ecosystem that we, the broader community of designing computing systems, all the way down from materials up to applications, architectures, all this kind of stuff. We have this whole ecosystem for energy efficient computing. And it makes me sort of think back, I hear stories of back in the day or whatever, people used to design computing systems and they didn't even care about the power or the energy consumption. They only worried about how, what the clock speed was, or how, get it to run as fast as possible. And there must have been some point where power became a problem, right? We were, whatever, melting stuff or frying batteries or something like that, and people realized this is a problem. We need to also consider energy consumption when we're designing our chips, right? And now we don't run stuff as fast as it possibly can. We make a nice trade-off between power and performance. And I think it feels to me, at least, like this is a sort of, that juncture is kind of coming up again with the carbon footprint, or at least I hope so, that people definitely realize this is a major problem now. And I think with ISCA community and communities above and below, in terms of the computing stack, we need to sort of bond together and come up with this similar ecosystem for carbon efficient computing.
So I think that we need simple metrics and methodologies. We have absolutely no idea of, as a computer architect, we propose designs, and what we do is we might talk about the amount of storage that we need for a particular microarchitectural contribution, or the amount, the number of watts that we're consuming in power, but we don't really have proper metrics and methodologies to guide researchers. And I don't think computer architects need really detailed models for fabrication costs, emissions, or very detailed model about the breakdown of, leakage current versus dynamic power. But we need just basic metrics and guidelines. Let's just take an example, right? We have online services in the data centers. You can run these online services on an Ice Lake core, which is 6 millimeter squares and 7 nanometer. You can run them on an Ampere, first generation of Ampere ARM cores, which are Neoverse ARM cores, stock cores. They're about 1.4 millimeters square. The Ice Lake has a phenomenally better IPC for that particular online service, assuming that you have your tail latency and SLO already covered, right? It's about a factor of 2 better, but the Ampere core, even though it's a factor of 2 worse than IPC, if you look at the throughput and the amount of power it's taken, it's an order of magnitude more efficient, both in area and in power, right? So what we need to look at in the data center is, okay, we have our SLO, we have our tail latency. How do we properly design this piece of silicon, our socket? How do we organize it so we maximize the throughput per watt, we maximize throughput per square millimeters, simple metrics, nothing complicated, while we're maintaining that SLO. And then we can do a comparison of now which is superior to other. And we don't have any such methodologies or practices in our community, which is a little bit mind-boggling.
Sounds like a good opportunity for computer architects. I guess tomorrow.
Okay, I think what I have to say relates to everything that you guys have said already. In terms of carbon, I really want to see us factoring in carbon cost in the design cycle. It's not only that we want to be able to analyze the carbon cost while we're designing a new system, a new chip or chiplet. And we have no good way of doing it today. And part of it is because of the transparency, the lack of data issue. But there are starting points. So there is a tool, which I think you're the co-author of that paper, which is called ACT, that is beginning to go in that direction. But it's not only that, it's also the trade-offs across the life cycle. So as I'm designing if I'm encoding something in hardware, and because I want to gain more operational efficiency, but then the problem is that I make the hardware more complicated, and because the hardware is more complicated, it's more costly. Oops. It's more costly to manufacture, and there is a clear correlation because as you have, for example, more density, more complexity, the yield goes down, and if the yield goes down, that means that the average carbon cost per unit goes up. So did I actually improve anything? That's the question. I gained in operational efficiency. Maybe there is enough use to justify the cost, the rising cost of the carbon. So that's the kind of trade-offs that we need to do, and there are lots of examples of this phenomena. For example, I don't know, look at memory, look at building redundancy in order to cope with the reliability issue, okay? And that's a good thing, right? But the carbon cost goes up, okay? So trade-offs. And then the other one is really when it comes to AI, I do think we need to focus on AI because it's here to stay. It's not going away. But there's so many interesting, this area is so ripe for innovation that it's really amazing. In particular, hardware and software co-design. As we look at, for example, the LLM architecture, can we incorporate energy as a guiding principle in designing a new LLM architecture? Can we have that as an objective when we're considering different optimization techniques, pruning, sparsity, quantization? Look at that, not just look at performance, but look also at energy. And can we have the hardware in the loop, actually? So knowing the hardware, because it actually runs differently on different hardwares. So there is this relationship between the LLM architecture and the hardware architecture that we don't really understand. We really also don't understand the relationship between complexity, which energy is correlated with complexity, and actual quality, right? The quality of the result. And even more interesting than that, like if we look at this community, the ISCA community, and we look at what we know from years and years of research on hardware architecture and rising complexity and having energy as a goal, can we apply these principles to LLM design? Because clearly we need to address this problem, right? Because it's just getting bigger and bigger, and it's not sustainable. So this is my two thoughts. I have another thought which is much more abstract about how we curb complexity. How do we curb complexity? And that, I think, is relating to metrics. The complexity is going to kill us with this diversification of hardware. And I guess that has to do with abstractions, with programming models, with metrics. But finding the right abstraction is really, really hard.
Really glad to hear that. I think there is some convergence on we need metrics and tools. Do you feel like there is sufficient tooling support? And if not, what are some new tools that you feel like our community need to build?
It's a really good question. I think in this community we've built amazing tools, and they've been they've had an impact, and they've been recognized also with awards over the years, right?
That's right.
Yeah, so I think that we're absolutely at a point where we need to find ways in which we can not just measure throughput and performance, which has been historically the metric of use, but also tools that allow us to measure for a particular service, and this is again in the context of data centers, but you could bring this into a mobile platform too, for a particular outcome of a service or an outcome of an application that will shed light into exactly what the energy footprint of that is. That energy footprint could be in fabrication, or it could be in operation. I also want to point out, by the way, now that we're in this topic, that in the case of the data center, AI has been a nightmare in terms of TDP. If you look at the power consumption, every chip that's coming out of NVIDIA, it's a Moore's law. It's just doubling every 2 years. I think that's also shifting, potentially shifting the balance between operational power versus fabrication power. But the TDPs of CPUs are also going up. I don't know if you've seen that. I wrote a blog recently. If you look at the latest CPUs that are coming out, the TDP of CPUs used to be around 100, 150 watts for quite some time, maybe 15 years. The latest CPUs, the TDPs are 300, 400, and they're shooting up. So this is sort of clearly showing that in the data center space, at least, that maybe the operational power is sort of going to dominate.
Yeah, I mean, I think in addition to the tools, which I think will come, obviously it needs effort, but I feel like there also needs to be some kind of like, at least in the small amount of time I've been researching in this area, it feels like it would benefit from some almost like consensus. This also gets back to some of the metrics, like what should we actually optimize for? Like when we, again, like as a community, we have very good sense of like when it makes sense to optimize for power, when you have a power constraint, maybe your battery is this big, or I want I want to be able to run this job for, 8 hours, and so I need to have, like, and my battery stores this much energy, so like I need to have some energy constraint on there. Or, I have a tail latency constraint, I need some like time limit there. But I think it's at least not as obvious to me yet, like how we really should like consider like carbon in the design constraint. Like, should we consider like some maximum carbon constraint like per device, or should we be, meeting a performance constraint while minimizing carbon, or somehow sort of having some carbon efficiency where you sort of optimize like the ratio of your clock speed relative to how much carbon it's consuming? How do you even like incentivize different people to sort of optimize for these metrics, right? Like as a consumer, I might have very like good incentive to buy something that has a long battery life, but I'm not sure that everybody in the world would care so much yet if like their computer had a low carbon footprint. So I think some of this sort of conceptual or like sort of community agreement on the importance of metrics, or at least understanding like which metrics to use, like in which scenarios, would also be very helpful.
Yeah, I think I'm going to reiterate Babak and others' comments about having tools, because Babak's example of 400 watts, that's now 400 watts for 96 to 128 cores versus 100 watts for 16 cores. So which one's better? These are all questions that I think if we had decent tools, decent metrics, we could answer. And I think that's the foundation upon which we have to build the whole carbon intensity aspects of this design.
Okay, so I also think that metric is extremely important. And one concept that is really important to understand is that we need to be able to measure actual work or good work rather than flops. Busy work, So I think what is missing, and this is, Babak, when you start talking about PUA, I totally understand what you mean, because what you're saying is, I don't know where the energy is going in the computation, And if I'm just measuring flops, I don't want to just measure flops. I want to actually measure the amount of work which is produced. The problem with measuring the amount of work which is produced is that it's specific. It's specific per application, and that's why it's so complicated. That's why it's so complicated to do the comparison, but it's important problem to address. And then if we look at AI specifically, then, how do you model, what is the amount of work which is being done? Some people measure tokens, so how much energy is being used per token. I can also look at inference jobs, but then how do I quantify across the life cycle? And I think that's what's important to understand here, that the way I look at it, I have a way of looking at it. I look at the model as a product, and I take concepts from the life cycle assessment, which means that there is a cost to create that model, and it's like the virtual embodied cost of that model, which is the training and the data preparation and all of that, all the work that has been put in creating that model. Then there is the jobs which are executing at runtime, the inference, but you want to amortize also the cost that went into the creation of the model into the cost of the jobs. So I think you want to actually look at the ratio. But I think the same thing holds when you look at carbon. You want to look at the life cycle of compute, and you want to amortize it based on the amount of work which is actually being produced, because it actually only makes sense to look at the ratio, because maybe you have a really low carbon cost, but you didn't use it at all. So, but maybe you have a high carbon cost, but you're using it so much, you're producing so much work, and the lifetime is so long that it actually pans out. So that's my few thoughts. I really agree that we need really good metrics and agree on them. Before we have good metrics, we can't build tools. And before we build tools, we also need transparency, because if we don't have transparency and we can't get the data, then we can't build tools. So that's the things we need.
Okay, I'm going to start asking attendees who have questions to line up at the mic, and also share your name, affiliation before your question. We are moving into the last part of our panel discussion, and that is, now should we have all the metrics and tools to guide the community on optimizing systems for sustainability beyond performance, power, cost, and all that? What do you see as some of the most important improvements that our community should bring to advance sustainable computing?
Let me see if I understand this question. I'm going to play my SDA hat, so Swiss Data Center Efficiency Association. What do? You showed a graph about where the breakdown of data centers are. Half of it globally is hyperscalers. The other half of them are non-hyperscalers. The hyperscalers, the electricity is factored into their cost of operation, so they try to properly load their equipment so that they get every bit out of it. But if you look at the other half, which is a co-locator market, and that's a big market in Europe, IT customers don't really have proper ways of consolidating workloads onto it. They buy equipment, they have racks, they have software, and there's a budget for it, and they go ahead and launch it. And if you ask the operator to say, well, electricity is cheap and we're just loading these. If you have, in Europe, there is a rating for appliances, there's a rating for cars, there's I don't know if you've seen this colorful A to G, right? If you get a washing machine that is AAA rated in terms of efficiency, and you run an entire cycle without anything in it, or maybe just one item, you're still wasting a lot of resources. And this is what we see the IT customers in our market are facing, which is they don't really know how to properly load for a particular outcome in the data center space their servers. And if we as a community establish best practices in properly consolidating workloads into racks, then a lot of these customers might find out that they can get away with half of the servers. So not only you're improving electricity consumption by a lot, you're also reducing your embodied carbon.
Okay, so I think I'm answering the question. So let me give you some examples of really innovative work that's happened in the architecture community before we ever even knew the word sustainability here. So simultaneous multi-threading. You can put 2 threads onto the same core for a small, tiny additional area cost, about 10 to 12% or so. That is a sustainable solution because now you can run 2 threads on the same core. Virtualization, another sustainable solution at the next level. I can now pack multiple VMs basically on the same node. At that point, I can use this more efficiently. So these are 2 solutions that are fundamental in how we build our systems and use them that really, we never thought about sustainability, but they have serious sustainability implications to them. So I guess what I would ask, in this community to think about now is, I think we can innovate. I think we can come up with ideas that are really cool. So going back to what Babak said about, utilization of these systems, many data centers, even large-scale hyperscaler data centers, if you only use them during the day and not at night, that's 50% utilization. And it's sometimes even less than that, because although the VMs are there, they're not always being run. So a lot of times these systems are kind of sitting around not doing much. So how can we address that problem? There are many papers out there on VM over provisioning, or over subscription, and how can we make VMs move fast and be able to land on systems quickly so that we can put more VMs in their physical cores? How can we reuse memory such that we don't have to allocate it to a VM, but we can reuse it as we're flipping VMs through? There's a lot of interesting research in this space where we can then use that to increase the utilization of our systems. Just some examples of ideas, but I'm sure there are many more out there.
Yeah, I just want to add to that. I think that we have the technologies, I agree. So we have virtualization, which helps you consolidate workloads. I don't think we have best practices as to how do you use virtualization to consolidate workloads and what your metrics are and what your methodologies. I give two examples. We've certified the Swiss Stock Exchange in Switzerland, and I was also at a conference where there were representatives of a German stock exchange. Their CPU utilizations are less than 10%. Okay, because they have certain requirements for replication, for data reliability, availability. They don't have proper methodologies to improve that consolidation with virtualization and still achieve their availability and reliability goals, right? And I think that's something that the computer systems community can help with, because these are proprietary know-hows. The hyperscalers know how to do this. I remember attending an ISCA conference when one of the networking experts from Google was saying, we keep our utilization low at 10% because that's the most important thing that matters to us, our SLOs. For the next 10 years, they realized that they're building too much, it's getting too expensive, and they developed consolidation technologies to reach much higher utilization with the same investment in equipment. That's a know-how that the academic community doesn't have, and we don't have best practices outside the proprietary knowledge of the hyperscalers.
Yeah, I agree that we have, in this community, we have so many low-level mechanisms that are absolutely brilliant. And I agree that a lot of times the complexity is in the next layer, which is how to use them, how to map, and also the problem becomes more and more that you have optimization techniques that are really specific across the stack for a particular model, a particular set of libraries in a particular system, and they're not composable. So just understand what to use, when and where and with what is a big problem. And I think more and more we're going to see an issue where you just don't have enough energy. So you're used to it from chip design, specifically for edge devices, working with power constraints. I believe we're going to see it in the data center level. There is just not going to be enough energy. And then the question becomes, how do you run the most work with the energy you need? And a big opportunity, which is, it's not specific to this community, but I'm going to mention it anyhow, is actually, because I think it's really important in the area of sustainable computing, is the fact that you have renewable energy. Net zero means I want to move to renewable energy. I want to just consume renewable energy, right? The problem with renewable energy is it's going up and down with the wind and the sun and so on, right? So what's going on is that the data centers are going and are asking for more and more capacity. We're actually seeing it. They're doubling the capacity, wanting more energy. There is no energy. The grid comes back and says we don't have enough energy. The problem with the renewable energy is that they can't guarantee a certain minimum. They can't because of these shifts. Well, think about it. Computing is flexible in the sense that we can move computation, we can power down, we can make it work slower with DVFS and all sorts of techniques, power capping and so on. So we're providing a buffer. So let's think about a city, let's think about a power grid, and let's think about a data center, okay? The power grid must provide critical services for the city, hospital and things like this. You can't move patients around, right? But what the way to handle it is that the data center need to grow and shrink based on the available energy. And that, in my opinion, that has to happen. That could be a big contribution if we understand how to do it. It could be a good contribution towards actually decarbonizing the grid.
I guess one other small thing I would add to this is I think that it will also be important to do predictive analysis of the potential benefits of future technologies that might not be in development yet or might not exist yet. Even in this regime that we're seeing now with various integration techniques or 3D integration or heterogeneous integration of different chiplets, like I would encourage people to explore like different possibilities that like aren't developed to show like which should be developed from a carbon efficiency point of view and maybe like which ones like should not be developed.
Cool, thank you. So please line up for questions for the panel and please introduce yourself.
I'll start. Paolo Faraboschi, HP. Carol started by saying that embedded carbon is very important, and then nobody talked about it. Everybody talked about reducing energy efficiency. So let me double click on that. One way to reduce the manufacturing cost is to extend the life of parts, right? So make them last longer. Unfortunately, this industry, and I don't want to shoot myself in the foot, is trying to push faster refresh cycles. Consumer electronics is an extreme of it, but even in the infrastructure, some companies are saying they want to build a new GPU every year. Now, is there anything this community can do to make things last longer and effectively extend the obsolescence of parts without shooting ourselves in the foot?
I think I talked a little bit about it. I mentioned the trade-offs across the life cycle. When it comes to an obvious example is memory. If you want to extend the life cycle of a memory device by making it more reliable, you build redundancy into the hardware. That's one mechanism, right? And that is a good thing. And that means that the carbon cost, the embodied carbon cost, is going to be amortized across much more use. So you effectively reduce the amortized carbon cost per unit of work, which is what you want to do. What you need to be careful of is the flip side of it, which is as you build redundancy into the hardware, you make the hardware more complicated, more complex, carbon cost goes up. So you must find the balance and you must find the trade-off across the life cycle. I totally agree with that.
So I don't think we're going to get into the economics of this because if you don't make money, you're not going to do it, right? But in the data center space, there's a lot of opportunity. So Carol presented a breakdown of embodied carbon in mobile devices from Apple. In a server, there are estimates that the majority of the carbon is coming from DIMMs, from DRAM. And with every generation of DRAM, of course, you have to throw everything away. With CXL fabrics, you can now recycle a lot of those older DRAM DIMMs that you had with DDR4 and create extended pooled memory in memory servers within your rack. So there are interesting technologies to pursue, and I think there are a lot of really young, energetic people in this community who are already looking into this.
So one thing I would say in terms of longevity of chips is that if you look at like adjacent spaces in computing, if you look at cars, for those spaces, you have to make chips that last 20 years. They have to be, regulated. They have to be, conditioned for that. So there is an entire space of technology where they are looking at longevity. It would be great for us in the general computing space to go and examine what's happening in that space. The second thing I would say in terms of embodied carbon is there are 4 things that matter, at least at a first order, for embodied carbon. The first is the area of the die. The second is basically the yield, okay? The third is the energy used by the manufacturing sites, whether it be TSMC or Intel or Global Foundries. And now I've lost my thread on the fourth one. But basically, if you can address any of those pieces of it, then you can also make a piece of silicon that has less embodied carbon. So think about how much of our space on our silicon is caches. Okay, do we need the caches? Is there a different way that we can design the caches? That we can start looking at those at a microarchitecture level also.
I'll just put one slight other spin on that and tying it back to the kind of metrics and optimization frameworks. Like even if you can't convince somebody to extend the lifetime of their product by beyond 2 years or something, maybe that then becomes like a constraint in your framework. And if you have models, good models for embodied carbon, maybe from circuit point of view, whatever, we have a more detailed model of every layer. Architectural point of view maybe has embodied carbon of DRAM or something. Then I feel like if you have the right modeling framework, then given that lifetime constraint, it would force the optimization result would be a system that had smaller embodied carbon. So I think it's maybe like another way that the models could help there.
Sorry, just real quick, I remember the fourth thing, which is a process technology node. So can we build this in an older node? For instance, would that be better embodied carbon? So just thought.
We have a long line.
Let me add one more thing, because
It's getting
Gabe, you
longer.
talked about it before, and I don't want this thought to be lost. You said chiplets, right? And I think that we really need to analyze what we gain when we move from system on chip to chiplets, also in terms of the embodied carbon. I don't have a clear answer. I know that there is one paper, but I can't reference it, that is starting to address it now. It's really important because there is more modularity, there is more reuse, and that may translate to embodied carbon efficiency.
Hello, Joseph Rogers, Norwegian University of Science and Technology. In terms of chip design, is it clear that simply optimizing for energy isn't already pretty much the same thing as optimizing for carbon? Because with dynamic energy, if you optimize for that, that's kind of your operational footprint, and static energy, a big way to optimize for that is the chip area. So when is optimizing for energy not the same thing as optimizing for carbon?
Yeah, I think that's a great question. I think there's a lot of parallels between actually dynamic energy and static energy and operational carbon and embodied carbon. That you see these same kind of, the same kind of thing that you would see in the energy consumption for clock frequency of a processor or power consumption, right? It's like you have your dynamic limited region and it flattens out to your leakage power. It's the same for lifetime, right? When you're limited by operation, and then the less you use it, flattens out to the embodied carbon. Yes, I think that you do still need both, right? The more embodied carbon operational, embodied carbon dominant you are, you do need to consider the fabrication more and more. And it's not just area, right? Like Bobby said, it's also the manufacturing process, right? Area is kind of a good proxy for it, to a high level, just dynamic energy is also a proxy for operational, but there's other things that come into it. Also, whatever, the system architecture, the chiplets, all this kind of stuff too.
And I guess there's also 3D stacking. That's not covered by area anymore. Yeah.
I think I'm not sure that I understood the question, but I think if you're just looking at operational and you're looking at the operation of the system, not the manufacturing of the system, and you ask for this operation, for the operation of the system, what's the difference between, it's the same. I think the operation, basically you consume electricity. So that's your source of carbon, okay? So the only difference here is if you actually in the computation factor in what's the source of the energy, and there are some body of work that is attempting to sense the source of energy because it keeps changing, and based on that adjust the computation. So that's a way to differentiate between energy and carbon in the operations phase, okay?
I guess the relationship between carbon intensity and energy may not be linear. Yeah. Cool. I guess let's move on to the next question.
Okay, Sandhya Dwarkadas, University of Virginia. So Paulo and the rest just addressed the issues, some of the devil's advocate issues of our throwaway culture and the fact that we want new technology every couple of years, right? So that's one aspect. But as panelists, you brought something else up, which was the utilization. And as you make things faster and cheaper and less energy, is it really that the energy consumption is going to go down, or are you just going to find people finding more uses for using the energy and more applications and more devices and more other things? So as architects, is there anything we can do about this? Do we need essentially to be working with policymakers, with other things? How do you address this?
Well, I mean, I could tell you from my experience with our customers, they do capacity provisioning. So they're not going to buy more. If they could properly consolidate their workloads into fewer servers and get the same exact outcome, they'll do it. But
yeah, I think, Sandhya, your question was about, well, if you make it cheaper, then are people just going to use more of it? And yeah, that seems to be the problem at the moment, doesn't it? I think, unfortunately, at some point, the economics have to come into the picture where it has to get expensive enough so that you don't trade it in regularly. But there are mechanisms that are in place that make it easier. For instance, every 2 years you get a new cell phone if you're on a Verizon or an AT&T plan. Do we really need a new cell phone every 2 years? But it's kind of built in to the economic model that they're using. So there are things that some companies can do to potentially fix that, but yeah, it's a really complicated problem.
Jalen Wong from Carnegie Mellon University. One thing that we've mentioned is obviously we need to care about operational and embodied emissions, and I think often there is potentially trade-offs between the two. So just as an example, we mentioned extending lifetimes, but newer hardware is potentially also more energy efficient, and so how you might navigate that trade-off space will also depend on how much is operational emissions in your system and how much is embodied. And I think maybe, and Tamara, I think, mentioned this, is that operational emissions is constantly shifting under your feet, where it depends on the region you're in, the time that you're operating at, both at long and short time scales. So I guess my question is, how do you all view how we can deploy and design systems to flexibly navigate that trade-off space?
I was going to say, Jalen, this is a great point for the metrics and models. So if anybody wants to pull that paper together, I think this will give us the points to, or the numbers to work with.
yeah, and Jalen, you yourself been working in this space, which is exactly, this is exactly what we need, right? We had a master's project in my lab where we took 4 generations of Intel servers and ran our workloads, the same workloads we use in the lab. And for some of the workloads, if you considered embodied carbon based on crude models and operational energy, taking into account a given amount of capacity in terms of throughput, for some of the workloads, even the 4th generation of Intel server did not break even in terms of total carbon. And in the case of some workloads, you could break even in 30, 20 years. We change servers every 5 years. We just work with the administration at EPFL where they updated their directives about how many years they need to keep servers, and they extended it because of this.
Thank you.
Okay. Elba Garza, University of Washington. I find this slide to be a bit disingenuous, the one that is up. I think y'all can see it there. I noticed that it says manufacturing, transport, product use, recycling. Who in this room does not have a drawer full of old technology? Is it getting recycled? Is it actually being sent to the proper places in order for, as Babak mentioned, there is some technology that we can recycle, but others that we cannot? Let's not even talk about the battery situation and the elements that we need to get in order to make everything electrical work. These are issues that we're not even talking about here, and I'm not even sure if it is supposed to be in this room. It's more materials, I'll admit. But do you think the companies that we work with, the companies that our students go to, have some kind of responsibility in ensuring that these materials and their resulting pollution gets addressed as part of the equation?
Mm-hmm. I totally agree that I think one of the things for sustainable computing, we need a multidisciplinary research, and that includes algorithms, hardware, software, all of that. It also includes material science. So, I mean, you gave me the perfect segue to do a little bit of advertisement, because we do have a program which is called PFACTS that we're running, IBM Research, together with universities and the nonprofit supported by NSF. It's a convergence accelerator, which is a project that is by design multidisciplinary. And the idea is, for example, to replace, it's not for example, the idea is exactly to replace PFAS materials. PFAS materials are very, very toxic. they're highly used in the manufacturing of chips, and the idea is to obviously use AI, because we always use AI, to identify where PFAS is being used, to accelerate the scientific discovery in order to find new materials to replace PFAS. I really believe in that we can actually accelerate scientific discovery with AI, which we really need, and then handle, like recycling better, the things that we can't replace. So that's PFACT. And so yeah, we're doing something. And I think when it comes to the design tools that we talked about, like designing new chips, I think one of the weaknesses of the work that was that started is like the ACT tool is it's not fine-grained enough to actually factor in if we find a new material, because it's just not fine-grained enough for that. But once we make progress with material science, I think the role of this community is to be able to take that input and incorporate it in design. That's what needs to happen.
Yeah, I think this also kind of like reminds me of another sort of way of thinking of this is that like improvements in recycling, I think fall into this category of like carbon efficient technologies or like technology innovations. And I always think back to like circuits type stuff or architecture stuff where there's only so much we can do with whatever, like a single core processor and some vanilla silicon technology. You can optimize that, right? But then there's these new technologies that come along the way, like multi-threading or like FinFETs or 3D integration that like enable you to have better trade-offs between like power and performance. That you're not just like optimizing stuff anymore. You have this like new technology that's like enabling more benefits. I think this like new recycling technologies can fall into that stuff with like carbon capture or like abatement. Like these things like fall into this like enabling better trade-offs. So there's like this optimization and the technology advancements.
So I just want to call out to one paper by Karen Strauss at Microsoft Research. She did a compostable PC board work. So if anybody wants a chance to take a look at that, it's actually a really interesting project a few years ago. And maybe somebody else here can come up with some innovative ways to design systems that we can, basically recycle easily.
David Wenslauf was working on biodegradable circuits several years ago.
Thanks, all.
If I can mention also that I think design with modularity in mind will make upcycling opportunity a lot more easily. And then there's also like the buyback program. So like, sell your devices back, don't just put it in your drawer, and then they'll incentivize companies to actually figure out how to recycle electronics at scale.
Conrad Lai, Intel. A lot of the things that brought up, do we need for our community? Do we really need to use the sustainability hammer to get people to work on it? Because try to get better yield on process, I won't be surprised the FMC have 100 people working on it without us motivating them, right? And same thing about consolidation, right? If people can do it, viable. It's not that people are not working on it, right? And we don't need the sustainability to really light a fire under them. But there are some problems that maybe these things are unique. You bring up that without this angle, people will never work on it, right? Like new material is not that people are not looking at new material, right? A lot of those depend on whether there's alternative in the next 5 years. And we can, this thing can help to accelerate, right?
So I'm going to go back to my hammer, and that hammer is that if you give a flashlight on the rack and tell the operator, here is a proper way of using this rack, that's for me, that's a hammer. That's the first step.
That's good for TCO, good for a lot of stuff, right? Right? More utilization, more profit, right? The finance guy were more than happy to fund that type of work, right? So what are the things that, like, we need the sustainability? Chemical pollution and some of those, right? Some of the corporations have to come in and just say, okay, I want it to be, get rid of some of the stuff. Like,
I don't think,
a lot of
is there a silver bullet? Yeah. I think, a bunch of things have to come together to push in this direction.
Yeah. So the other thing is, a lot of those seems the solution is in the business, right? They say, LLM, if people are willing to pay, unless you have some other structure, the demand is going to go through the roof. Of course.
So Conrad, there are several cities that have moratorium on building data centers because they're out of electricity.
No, so yeah. I agree, because some of the people don't change because they are limited, because people replacing the computer because, okay, I only have like 100 megawatt in this data center. Like you suggest about keeping the system for a long time. It's viable, but they just need to throw those things away so they can put a new system that would make more money. It's not that those are not good enough.
That's why I said that we're not going to talk about the economics of it,
yeah,
right?
So
That's
I
a completely different
I try to separate the things, more like focus on what are the things that our technical people, that if sustainability is not the angle, we're not looking at it, right? Because a lot of those topics people have been working here for their own self-interest or for other justification, right? If it's not there yet, it's not they're not working on it hard enough, right? I cannot say, hey, they are lazy, right? They have been working on it for a long time.
I think the point here is that science is not enough in technology. We need also incentives and policy, which I totally agree with. And I think this point came up in the NSF workshop that we had on sustainable computing very loud and clear. So, yeah.
Okay, we are towards the end of the panel. If I can invite just, we can have 2 more questions and then we'll close this out. And feel free to continue discussion during excursion, during banquet and all that, okay?
It's not a question, it's more of a comment.
Okay.
The previous discussion about incentives, I just wanted to bring up the comment that every time we submit something about sustainability within this community, for some reason the reviews tend to talk about how does this even matter from an economics perspective, and as system designers we're forced to somehow reckon with the reviewers about the economics, which is interesting, but also kind of orthogonal to doing systems research and sustainability. So just wanted to make people aware that as a reviewer, encourage sustainability research from the systems perspective, even if the economics might not always add up. Thanks.
Luca Carlone, Columbia University. Thank you very much. Very interesting panel. And I missed the first part, so I don't know if what I asked has been discussed. But as we develop better model to account for sustainability, and maybe there is a needed model for different class of systems at various levels, from the computer system to the chip, different type of chip. Have people thought about accounting for the benefits of computing with respect to sustainability in the environment, how you can quantify that as part of the equation? Like, for instance, let's have more Zoom meetings than travel by car or by plane, but that's a simple example, of course.
Barely hear you. Get closer to the mic.
We couldn't hear the question.
Do I speak? I have to speak louder.
Okay, yeah.
Okay, sorry. First, I repeat. I apologize because I missed the first part of the panel. Very interesting. As people are developing model, which I try to, as I understand it, to quantify the issue of sustainability and the cost and the impact on the environment, are people trying to quantify also the benefits that computing, a different class of computing, may provide with respect to an environment perspective and sustainability perspective? So, for instance, you can have more Zoom meetings and travel less. That seems, approximately, I haven't studied the problem, seems to have a good impact. And I guess different classes of systems at different level, more vertical and horizontally, provide different types of positive impact, which to a certain extent should offset the equation, or is not an issue. That is taken as a given, and we are just trying to save as much as possible on the other side.
I think this goes back to the comment made by the panelist earlier about you have to think about what is of value versus what is not. I love dancing cats, but honestly, that might not be the best use of AI. But if you use AI to determine how best to deliver electricity on the grid, on optimization, which it is being used for these days, and it's a fabulous use for it, it can have a lot of benefits in terms of being able to have much more efficient power supply and grid systems. So there are significant benefits to AI. Unfortunately, this community can't dictate whether it's going to be dancing cats or electric grid optimization that's going to be used for.
So just a quick one. An optimization in data center space that's quite popular in Europe is heat recycling networks. So we're building data centers not just next to sources of electricity, networking, and water, but also heat recycling networks that are zone-oriented. And we have KPIs to show that that actually has an impact.
That's an example. It seems that also going beyond data center only, which is very important, thinking also about all the embedded systems that were mentioned before and the personal computing, the equation can be fairly complex, no? But should be considered.
I guess one thing I also maybe understood from your question was like if you were going to actually use computing to even figure out what was the most sustainable way to do computing, right? Like, I mean, almost like sustainability mining.
And I guess the progress in a lot of
like maybe
sustainable source of energy comes also thanks to computing. So I think there is this issue now of balancing the need for us to do better with the fact of also portraying how the community is helping and try to have both aspects, just not to be just apologetic in some sense.
I want to throw a stat out there. If you look at the amount of renewable energy that is being curtailed on the power grid, it's 15%. That's a lot of free renewable energy that can be useful, but we couldn't really figure out a good way to unlock those renewable energy. And that's, I guess, goes back to like how AI can be helpful if we can do better forecasting, and how computing, if it's more flexible, then we may be able to use those renewable energy that is currently not being used.
Smarter cities.
Cool.
Thanks.
So I want to take the opportunity to thank our panel again, and thanks everyone for attending it. Thanks. I guess, Rajiv, do we have logistic updates on excursion? The other one?
Thank you. Just a reminder to everybody that the excursion begins at 7, so that's when you should be, I think, lining up. Yeah, lobby at 7, and that's where we'll be boarding the buses. Is Augusto here? Is anything else we need to say? Okay, I think that's it. Yeah, and don't forget to bring your ticket for the excursion. Thanks, everybody. Thanks. Really good panel. Thanks.
Carol, writing a blog is also super good.
Oh, yes. So we can like organize our thoughts.